Okay, since we have only 1 hour today, so I will try to go through just a few stuff in the next subtopic, which is 5.2. Okay, before we start, I just want to remind you that I have assigned the individual assignment on GC. Kami sudah assign before this on Saturday. Actually, ada perubahan dengan soalan tu. So, Miss sudah assign semula tadi. So, yang Miss upload balik tu adalah soalan yang sudah di-update lah. So, soalan yang sebelum ni kamu jangan guna yang tu sebab ada certain words yang mengelirukan. So, sudah diubah. So assignment due minggu depan hari Jumaat right before mid-sem 4 March due jam 5 PM. So kalau lambat you will be penalised. So make sure kamu ada 2 minggu kan untuk buat assignment. So make sure buatlah yang buat awal so that nanti bila mau submit tu tiada masalah lain. So boleh submit dengan awal. Okay, so soalan yang sebelum ni boleh ignore. Kalau siapa yang sudah download tu boleh ignore that one and then download semula yang Miss sudah upload tadi. Okay. So kita akan sambung 5.2, subtopik 5.2, Induced EMF. So hopefully kamu sudah tengok video yang Miss bagi minggu lepas, which is kita sudah cover subtopik 5.1, Magnetic Flux. Okay, so basically what we are going to look at this subtopic is that we are going to see what is induced EMF and how can we produce this induced EMF. Okay, before we go into detail what is induced EMF, okay, kita recap dulu apa yang kita pernah belajar sebelum ni di dalam chapter 3, which is about EMF. Okay, EMF ataupun nama panjang dia adalah electromotive force. Walaupun nama dia force, it is actually not a type of force. It is, by definition, it is the energy transfer in driving one unit of charge around a complete circuit. So we learned before in DC circuit that in order for us to distribute electricity, okay, we can connect the component to a battery. So let's say component kita dekat sini adalah bulb. So when we connect it to the battery, so this is the battery, we notice that there is a current flow throughout the circuit and then this bulb will light up. So this is one way to distribute electricity. We connect to a battery, to a chemical, to a power supply. Okay. Based on this definition, the battery actually supply energy to the charge in the circuit. So they supply energy. Actually dia bukanlah force, they supply energy. So that charge tu boleh bergerak daripada positive plate and then complete one circuit. Complete balik and then patah balik kepada negative plate. So that is what we call as electromotive force, the energy provided by the battery. So, based on this definition, we can say that it is energy per unit charge. Di mana energy per unit charge, we learn in chapter 1, it is equal to potential ataupun voltage. So, electromotive force is indeed a type of voltage. So, dia adalah salah satu contoh voltage. So this is what we learned in chapter 3. Okay. In chapter 4, we learn about magnetic field. Okay, di mana when we have a conductor, so this is in chapter 4 about magnetic field. When we have a conductor carrying a current, okay, conductor tu mesti carry a current and then we can observe that this conductor, this current actually, the current will produce magnetic field, okay, around the conductor. Okay, this is the magnetic field line. Okay, so from here we can say that current can produce magnetic field. Okay. In this subtopic, what we are going to see is the other way around. Is it possible for the magnetic field to produce a current without connecting the circuit to a battery? Sebab before this I said, okay, kita kena connect dengan battery barulah battery ni boleh supply energy dan kita punya bulb ni akan menyala. Now, we want it to be the other way around. We want the magnetic field to produce electricity, to produce current without connecting it to a battery. So this is what we are going to see in 5.2. Okay. Perkataan induce di sini bermaksud, Miss cakap tadi EMF ni adalah type of voltage, right? So induce voltage, kita boleh cakap lah, induce voltage is actually a voltage that is produced from magnetic field. Okay, from magnetic field. Macam mana kita membuat benda ni? Okay, so this induced EMF is first discovered by a scientist named Michael Faraday. So that's why dekat sini kita akan apply Faraday's law. So Michael Faraday ni dia buat satu eksperimen and dia discover, oh, we can produce electricity from the magnetic field without connecting to a battery. So how does Michael Faraday do this? Okay, macam mana dia discover benda ni? So the experiment, okay, this is the setup of the experiment Michael Faraday buat. So apa yang dia buat? Okay, dia ambil satu magnet sebab kita tahu magnet ni ada magnetic field. So there is a magnetic field. So magnetic field tu dia from north to south. And then dia ambil satu, actually the original experiment Michael Faraday buat adalah dia gunakan galvanometer sebab galvanometer boleh detect current. Tapi sekarang ni tak best lah kan kalau kita guna galvanometer, so kita gunakan bulb di sini sebab daripada bulb ni kita boleh tengok lah kalau dia menyala maksudnya ada current. So bulb ni dia connect kepada coil. So this is a coil with a few turns here. So there's no battery here. Tiada battery. So dia buat, dia letakkan magnet berdekatan dengan coil ni. So apa yang dia first discover, nothing happen. Okay, dia letak magnet. Okay, magnet ni kita tahu dia ada magnetic field. And then dia letak sebelah coil. Nothing happen. There is no current because the bulb doesn't light up. And then the scientists try to move this magnet near to the coil. So dia discover lah, or dia dapat dia notice, oh, the bulb is now light up. Maksudnya apabila dia dekatkan magnet ni kepada coil, the current will flow throughout the circuit. That's why the bulb will light up. But as you can see here, if the magnet is inserted inside the coil tapi tiada pergerakan, dia letak je macam ni. So they discover there is no current. So from here, dia dapat concludekan bahawa apabila kita gerakkan magnet berdekatan dengan coil, barulah akan ada electricity, barulah kita boleh produce electricity. So the key here is the magnet must keep on moving. Kalau dia berhenti je, there's no electricity. Okay, so from here we can see that, okay, initially dia dekat sini kan. So daripada voltmeter ni kita boleh tengoklah deflection ke positive and negative direction tu. So kalau kita dekatkan dia akan jadi negatif. So menjauhi, dia akan jadi positif. Okay, mendekati coil akan jadi negatif. Menjauhi coil, dia akan jadi positif. Okay, now let's see if we have a different coil with less number of turn. So apabila kita letak dekat sini, gerakan dia, as you can see, bulb tu dia menyala tapi berbeza dengan yang number of turn dia lebih banyak, bulb tu menyala dengan lebih terang. So more number of turn will produce more electricity here. Okay, they can produce more current. So this is what Michael Faraday punya experiment lah. They just they basically gunakan coil and then they connect dengan galvanometer. Okay, original experiment dia adalah guna galvanometer. So this one ada dalam nota kamu instead of they gunakan bulb. Okay, so from here, Faraday says that okay, we can produce current daripada magnetic field. So this is just a simulation untuk kamu tengok dengan lebih jelas lah. So when we have magnet and then we move it near to the coil. So in this case, this one is actually solenoid. Benda yang sama juga. There is a wire yang dililit dekat conductor. So benda ni berlaku sebenarnya sebab apa? Okay, we want to find out what actually causes the magnetic field to produce the current. Okay, so lepas Michael Faraday ni sudah kaji, okay, dia dapati bahawa the change here, dia dapati bahawa there is a change in magnetic field actually. There is a change in magnetic field. So apabila ada perubahan dalam magnetic field, akan ada perubahan dalam magnetic flux. Okay, magnetic flux, we learn it in first subtopic 5.1. Apabila ada perubahan dalam magnetic flux, since magnetic flux is a BA cos theta, okay, apabila ada perubahan dalam magnetic flux, maka terhasilnya voltage, terhasilnya EMF. So, bila ada EMF, okay, macam yang Miss cakap tadi, EMF ni dia supply energy so that current will flow. So, bila ada EMF automatic, akan ada current. So, here we can see a deflection of the galvanometer. Maksudnya akan ada current flowing through the circuit here. So, as you can see, there is no battery here. So, dia dapat energy tu daripada moving the magnet next to the solenoid or the coil. Okay, so daripada sini Faraday's law dia conclude that the magnitude of the induced EMF in a coil is directly proportional to the rate of change of magnetic flux of the coil. So Faraday's law hanya menyentuh tentang magnitude of the induced EMF saja. So dia cakap induced EMF ni directly proportional to the rate of change of magnetic flux. Okay, notice here rate of change maksudnya perubahan in time. There is a change in time in magnetic flux of the coil. So we can write it down as this formula di mana EMF is equal to d phi. So this one, simbol ni adalah phi, kita panggil dia phi. I think ejaan dia PHI. d phi over dt. So perubahan magnetic flux in time. Okay, so negatif ni nanti kejap lagi Miss akan explain. So according to Faraday's law, induced EMF directly proportional to the rate of change of magnetic flux of the coil. So the higher the rate of change of magnetic flux, the more induced EMF will be produced. Okay, sebab dia directly proportional. Okay, so far jelas? Ada soalan?
Jelas, so far jelas, Miss.
Jelas.
Jelas, Miss.
Okay. So dalam induced EMF ni, we are going to apply another laws. We call it as Lenz's law. Di mana Lenz's law ni akan menentukan direction of the induced current. So Faraday's law tadi dia just sentuh pasal magnitude sahaja. Lenz's law dia akan sentuh pasal direction. Okay, so according to Lenz's law, the induced current will flow in a direction such that the magnetic field produced by the induced current will always oppose the changing magnetic flux that produces the induced current. Okay, basically apa yang Lenz law ni cakap, I don't like changes here. Okay, sebab kita tadi Faraday's law cakap we need to change. Okay, we need to change the magnetic field so that we can induce EMF. Therefore, we can induce current. But then these changes, Lenz law kata I don't like these changes. So apa yang dia buat dia kena oppose the change. So the keyword here, the Lenz law need to oppose the change in the magnetic flux. So macam mana dia oppose the change? First, if the magnet is going towards the solenoid or the coil, dia kena oppose. Dia cakap, oh I don't like you to come closer to me. I need to push you away. So dia terlalu dekat kan? So dia kenalah tolak magnet ni. So dia tidak suka ada perubahan. So macam mana dia tolak? Since dekat sini, okay, according to this diagram, since dekat sini dia adalah north, so the side here akan automatic jadi north juga. So dia akan jadi north. Sebab bila north bertemu north, dia akan repel each other. So kalau dekat sini north, dekat sini akan jadi south. So this is the case when the magnet is moving towards the solenoid. So V dekat sini maksudnya pergerakan lah, ada velocity, pergerakan mendekati solenoid. But if the magnet is moving away from the solenoid, and then solenoid Lenz law cakap, no, I don't like you to go away from me. Okay, you need to come back. Okay, dah boleh jauh-jauh lah, so kena dekat balik. So macam mana dia mau tarik balik magnet ni? Dekat sini dia kena jadi south. Sebab north dia akan attracted to the south. So kalau dekat sini south, automatic. Dekat sini akan jadi north. Okay, so daripada sini setelah kita sudah determine north and south di sini, we can determine the direction of that induced current. So direction of that induced current we can determine using right hand grip rule. So this one we have learned in chapter 4. Okay, so kita akan gunakan right hand grip rule di mana our thumb will be the direction of the north. Thumb will always be the direction of the north and finger will be the direction of the current. So how can we do this? Kita boleh gunakan pencil. Okay, so ikut contoh ni, north dia pergi kanan kan? So our thumb must be pointing to the right. So apabila pointing to the right, okay, semua buat ya. Apabila pointing to the right, you can see that your finger ada di belakang pensel kamu. Okay, apabila dia di belakang, maksudnya finger tu dia pergi belakang and then dia pergi depan. So direction of current tu adalah daripada belakang wire and then dia naik pergi depan. Daripada belakang ni adalah dekat belakang sebab kita nak nampak kan. Dia akan pergi belakang, daripada belakang and then dia naik, dia turun pergi depan. Macam tu. So this will be the direction of the current. Okay, boleh semua buat?
Boleh, Miss.
Boleh, Miss.
Okay, so this one is when we have north pointing to the right. Okay, next one when we have north pointing to the left. So sama juga. This time, bila kita punya thumb pointing to the left, we can see that kita punya finger, dia akan naik daripada depan and then pergi belakang. Maksudnya current tu dia akan naik daripada depan dulu. So depan dekat sini we have the wire. So from here, then dia akan turun ke bawah macam tu. So, akan naik macam ni. And then turun ke bawah. Okay, so from here, if you notice here, in the first case, when we have the magnet moving towards the solenoid, okay, deflection dia pergi kanan. And then when it is away from the solenoid, so deflection dia opposite direction. Okay, deflection ni doesn't matter actually. Kita tidak tekankan sangat mana satu deflection dia. Just that kita tahu, okay, kalau first kita dekatkan magnet ni kepada solenoid, okay, deflection dia pergi tempat ni. Maybe kanan atau kiri, okay, we don't know. And then bila kita jauhkan, dia mesti opposite. Okay, dia tidak sudah sama direction. Okay, boleh faham?
Boleh, Miss.
Okay, so since Lenz's law tu cakap dia mesti oppose the changing of the magnetic flux, that's why di dalam Faraday's law kita ada negative value di sini, negative sign. So this negative sign is just to indicate that the direction of the EMF is to oppose that changes. But in calculation, we can just ignore this negative sign. Kita tidak akan gunakanlah negative sign. It's just that Faraday's law letak macam tu je lah. Sebab dia take note apa yang Lenz's law cakap. So basically, Faraday's law akan cakap pasal magnitude, Lenz's law akan cakap pasal direction. So that's the difference between these two laws. Tetapi dua-duanya bercakap pasal induced EMF. Okay, so induced EMF ni kita boleh increase through a few methods. First, we can use a stronger magnet. So when we have a stronger magnet, meaning that we can increase the magnetic flux. Okay, we can increase the magnetic flux. Second one is when we push the magnet faster into the coil. So maksudnya dia kena lebih cepat so that dia boleh increase more, dia boleh produce more voltage. Next one, to use a coil with greater area. So the area of the coil must be greater. So lebih tinggi area tu, lebih banyaklah kita boleh produce EMF. And then last one is we increase the number of turns. So macam yang Miss tunjuk tadi, when we have more turns, we can produce the light, the bulb will be brighter. So maksudnya bila dia brighter tu, dia akan produce more EMF. More EMF meaning that more current. Okay. So induced EMF, okay, we can generate induced EMF through three things. First, melalui straight conductor, melalui rotating coil, which is application dia adalah dynamo and generator, and then melalui coil. Okay, so daripada sini kita tengok the first one is through the coil. So through the coil, we have two different changes that we are going to look into. First one is when there is a change in magnetic field. So untuk cari induced EMF di dalam coil, kita akan gunakan this formula di mana negative NA cos theta dB over dt. Since magnetic field yang berubah, so that's why kita guna dB over dt. So area dia akan constant. Di mana perubahan magnetic field ni is just that magnetic field final tolak magnetic field initial divided by the change in time. So macam mana kita tahu ada perubahan magnetic field? Selnya dalam soalan dia akan mention lah, ataupun kalau dalam gambar aja dia akan mention macam ni. So initially, so this is a coil and this is the magnetic field. So ni indicate represent magnetic field lah into the page. And then magnetic field ni, dalam coil ni, so coil ni this one, right? Dalam coil ni adalah magnetic field ni, dia akan go through the coil here. Dia bulat dekat coil ni. So compared to the final one, kita nampak dekat sini ada 4 dot saja kan, ada 4x di sini. So maksudnya magnetic field dia semakin decrease compared to the first one. So from here, maybe the first one is 2 Tesla, maybe final one is 0.1 Tesla. So from here, area still sama. Okay, kita punya magnetic field ni, kita punya coil ni still sama area dia. Area yang dia ambil masih sama, yang berubah hanyalah magnetic field sahaja. So this will be the formula di mana Still kita akan ignore the negative one. So di mana N di sini adalah number of turn, A is just the area, and then this one is dB over dt. Theta dekat sini adalah the angle between the area and the magnetic field. Okay, next one is when we have a change of area. Maksudnya, magnetic field akan constant. So, instead of tadi dB over dt kan, now we have dA over dt, di mana the change in area is just area final minus area initial. So, the area, the formula for area untuk coil is pi r square, ataupun kalau kita guna in terms of diameter, pi over 4d square. So how can we notice the change of area dekat sini? So magnetic field kita constant. As you can see here, magnetic field still sama. But now area from this one to this one. So area sekarang ni kecil sudah. Okay, so from here we can say that the area has changed. So apa yang berubah dengan yang tadi, formula yang tadi dekat sini, kalau area constant, so A dekat depan lah. Kalau B constant, magnetic field constant, B akan dekat belakang. This one, meaning that there is a change in that specific term. Kalau change in area, dA over dt, change in magnetic field, dB over dt. Okay, that one is for coil. Next one is for stud conductor. Kita ada satu saja formula, di mana EMF is equal to LVB sin theta. L is the length of the conductor, V is the velocity, B is the magnetic field, and theta here is the angle between velocity and the magnetic field. And for rotating coil, since rotating coil dia sentiasa rotate, right? So dekat sini we have the angular frequency. So EMF is equal to NAB omega sin omega t, ataupun omega t is actually the same as the angle. So we can produce maximum EMF, okay, when sin theta is equal to 1, ataupun apabila angle, when angle is equal to 90 degrees, since sin 90 adalah sama dengan 1, ataupun when the WT omega t is sama dengan 1. That's when we can produce the maximum EMF. So untuk this one, when we calculate this one, your calculator must be in degree mode. Okay, dia bukan dalam radian lah, walaupun kita gunakan angular frequency di sini. So ada 3 formula yang kita akan gunakan to calculate the induced EMF based on what type of conductor we have. Kita ada coil, straight conductor, and rotating coil. Okay, any questions so far?
No question.
So far, no question.
So far, no question. Okay, so kalau tidak soalan, kita boleh tengok terus kepada example. Okay, first example 6 here. So we are given 3 loops of wire. They are all in a region of space with a uniform magnetic field. Loop 1 swings back and forth as the bob on the simple pendulum. Loop 2 rotates about a vertical axis, and loop 3 oscillates vertically on the end of a spring. Which loop or loops have a magnetic flux that changes with time? Explain your answer. So we are given 3 loops here. Semuanya ada loops. Okay, satu ni dia akan move back and forth macam ni. Satu dia akan rotate, satu lagi dia akan up and down. So which one do you think will have a change in magnetic flux with time?
Yang ada spring tu, Miss.
Yang ada spring. Why?
Sebab dia pergerakan linear ke atas dan ke bawah.
Pergerakan dia atas bawah. Okay, yang lain
Sebab dia keep moving, Miss.
dia keep moving. Yang lain pun keep moving juga. So how do you know loop number 3 is the one that has a change in magnetic flux with time? Maksudnya akan ada d theta over dt. There is a change in magnetic flux with time. Okay, the only way for us to see this one, okay, macam yang Miss cakap tadi, in order for the magnetic flux to change, there must be a change. Okay, in first subtopic, we know that magnetic flux is BA cos theta. So angle dekat sini berperanan sebagai perubahan kepada magnetic flux. So kalau angle tu 0 degree, cos 0 sama dengan berapa? Cos 0 1 ke? So kalau angle tu adalah 0, kita tidak akan produce magnetic flux. So from here, untuk tengok dia dengan lebih jelas, kita lukis. Okay, kita lukis semula the plane of the coil. So loop yang pertama, let's say we have magnetic field to the right, and then kita letak plane ni macam ni, plane of the coil like this. And then we know that the area will always perpendicular to the plane. Now this plane is moving back and forth, pergi kanan, pergi kiri. So adakah perubahan angle di sini?
Tiada, Miss.
Okay,
Tiada,
tiada.
Miss.
Tiada perubahan angle. So there's no change in angle. And then loop number 2. So we have a uniform magnetic field. Sebab dia sudah mention, right? It is a uniform magnetic field. So B ni constant. Yang akan berubah adalah the angle between these two. Okay, now we have the same plane. Now this plane will rotate. Maksudnya dia akan pusing macam ni. So apabila dia pusing, it doesn't matter lah which one, clockwise or anti-clockwise. Apabila dia pusing, is there a change in the angle?
No.
Yes.
No? Yes.
Think ada.
Akan
Macam
ada kan?
ada, Miss.
Macam ada. Okay, macam mana
Ada,
kita
Miss.
tahu ada ke tidak? Okay, contohlah. Initially, I put it like this. And then, we want it to rotate, right? So maybe dia akan rotate macam ni. So from here, there is a change in the angle between B and A. So dekat sini akan ada perubahan angle. There is a change in angle because dia rotate macam tu. Dia tidak bergerak macam yang first one. First one is just from here to here. This one kita akan rotate. And then loop number 3. Nak buat pula. Okay, loop number 3. So this is the plane of the coil, and then this is the area. Now this plane, we will move it up and down, atas dan ke bawah. Is there a change in the angle?
No.
No, Miss.
No, right? There is no change in the angle. So, kalau tiada change in the angle, maksudnya kita punya magnetic flux pun tidak akan berubah, tetap sama. Selepas 5 saat, kita buat dia kan, dia bergerak. Angle dia still sama, so maksudnya magnetic field dia pun still sama. Ni pun sama juga. Up and down, selepas 5 saat, no changes in the magnetic flux as well. So the only change we can observe is when the coil is rotating. Okay, the coil must rotate. So maybe initially dia macam ni kan, 90 degree. So when after 5 second, dia sudah macam ni. There is maybe 60 degree of angle here. So apabila kita punya angle berubah, maksudnya kita punya magnetic flux pun akan berubah. Okay, so here we can say that loop 2 is the loop that has a change in magnetic flux with time. Okay, so from here we can say that the orientation not orientation. Loop 2 changes the orientation relative to the field. Maksudnya, there is a change in angle between area and magnetic field. So hence, the magnetic flux will change with time.
Miss,
Yes.
yang loop 3 ni kan, kalau dia turun dan naik, bukan dia potong magnetic flux kah?
Actually, yes, they potong magnetic flux, but kalau dia potong magnetic flux, should be kalau dia potong magnetic flux, dia akan ada perubahan lah, maksudnya akan ada perubahan magnetic flux. But I'm not sure. Let me KIV this one first. But as far as I know, there must be a change in angle first, so that there is a change in magnetic flux. Sebab dalam case ni, kita ada uniform magnetic field, right? But let me KIV this one first, and then I will get back to you in our next class. Okay? So for now, yang confirm, loop 2, loop 1 memang tiada. Loop 2 akan ada. Okay, akan ada perubahan. Okay, any other question?
No, Miss.
Okay.
No, Miss.
If there's no question, let's see example 7 here. Okay, example 7. The magnetic flux passing through a single turn of a coil is increased quickly but steadily at a rate of 5 exponent negative 2 Weber per second. If the coil have 500 turns, calculate the magnitude of the induced EMF in the coil. Okay. So the information that we are given is this value here. So you are given this value and also this value. Okay, so the first value represent what they quantify what unit actually. Okay, notice here we have Weber per second. So kalau Weber per second, it is
Induced EMF.
EMF. Is it EMF?
Induced EMF.
Induced EMF? No, it's not induced EMF.
dV over dt.
dV, okay, dV over dt. Actually betul lah juga induced EMF, but I want it to be specific. It is dV over dt. is equal to 5 exponent negative 2 Weber per second. Since magnetic flux, dia punya unit adalah Weber ataupun Weber lah, ataupun Tesla meter square. And then time is just second. And since according to Faraday's law, induced EMF is equal to dV over dt. Okay, so in this soalan, this number represent for a single turn of coil only. Now we have 500 turns. Kalau kita ada 500 turns, we just darab sahaja dengan number of turn. This one for single turn, now we have 500 turns, you just darab dengan 500. It's very simple. So EMF you will get equal to
25 meters.
25 volt. So EMF kalau dia minta EMF, kita gunakan volt ya instead of this one. Kita akan gunakan volt sebab it's voltage, right? Okay, so this one is very straightforward. It's just that you need to see lah here. Kadang-kadang kamu tidak perasan. You just assume this is actually adalah magnetic flux. But from the unit, kita boleh nampak it is per second. So kalau per second maksudnya divided by dt. Okay, divided by the change in time. Okay, let's look at the next example. Okay, this one adalah example untuk coil. Okay, so we are given here a coil having an area at centimeter square and 50 turns lies perpendicularly to magnetic field 0.2 Tesla. If the magnetic flux density is steadily reduced to 0, taking 5 seconds, determine the initial magnetic flux linkage and the induced EMF. Okay, first thing we need to do, let's keluarkan information. So we have area here at centimeter square. Okay, terus convert kepada meter. And then we have the number of turns, 50. And then the magnetic field. And then we have the magnetic flux density. Maksudnya magnetic field ni lah, reduced to 0. So initially dia adalah 0.2 Tesla and then it will be reduced to 0 Tesla. And then it will reduce in 5 seconds. Now determine the initial magnetic flux linkage. So there is a term linkage here. Linkage bermaksud kita kena darab dengan number of turn. This one Miss ada explain dalam first subtopic. So the magnetic flux is like this, right? BA cos theta. If we want it to be magnetic flux linkage, we need to times with the number of turn. Okay, so now we are given, sebab dia minta initial saja, so kita akan gunakan B initial and we have the magnetic, the area as well. So you just masukkan saja 0.2 darab dengan area. And then cos, okay, what is the angle here? What is the angle here?
Zero.
0. Okay,
90.
so from here, it's not 90 ya. Dia cakap a coil lies perpendicular to the magnetic field. Maksudnya, this is our magnetic field. And then coil 2 lies perpendicular. So from here, B dengan A akan jadi sama dengan kosong. Angle B between A is equal to 0. It's not 90. And then times with the number of turn, 50. So kamu akan dapat
At exponent
Kita ada
negative
kuliah
3.
negatif 3.
at exponent negative 3 Weber. Is it? Betul kan?
Yes, Miss.
Yes, Miss.
Okay. So that one is the first one. Second one, we need to determine the induced EMF. What is induced EMF? So dalam kes ni, yang berubah adalah magnetic field. So initial dia adalah 0.2 and then dia ubah kepada kosong. Okay, so dekat sini actually sudah dibagi the formula. Di mana E induced is negative NA cos theta dB over dt. So we just masukkan saja. N is 50, area is at exponent negative 4. Angle is 0. And then dB over dt adalah final minus initial. Kita mesti final minus initial divided by 0 minus 5. So initial time juga adalah kosong lah. Is it? Sorry. Balik. Final minus initial. So induced EMF kamu akan dapat
Miss, time bukan 0.50 ke?
0.5. Oh, sorry. This one, right? Okay. 0.5 second. 0.5 minus 0.
Zero point zero 0.016.
0.016 volt. Semua dapat?
Dapat, Miss.
Dapat.
Okay, kalau kamu dapat negatif, you can just ignore that negative actually sebab dia minta magnitude saja. So if you get negative, you can put that negative, letak negative sign pun tidak apa. Because in the end dia minta, soalan hanya minta magnitude sahaja. Okay, so untuk soalan ni, this is when there is a change in the magnetic field. So senang je lah, you just have to use the formula di mana kita ada dB over dt. And then dB over dt is just final minus initial. Okay, there's another two formula untuk coil. Okay, tapi kita ada 10 minit lagi, sempat ke? Okay, I don't think sempat sebab kamu ada kelas after this. So untuk example yang seterusnya ada lagi dua. For this one, okay, boleh cuba buat dulu sendiri. Tengok kamu dapat ke tidak. And then untuk kelas yang seterusnya, misalkan bincang semula. Okay, example 2 dan 3. This one masih di bawah coil juga. Cuma perubahan dia berbeza lah berbanding yang soalan 1. Soalan 1 perubahan dalam magnetic field. So soalan 2 nanti kamu baca lah dan soalan 3. Okay. Okay, so far clear kah?
Clear, Miss.
Clear, Miss.
Okay, so kalau clear, okay, make sure kamu fahamkan macam mana proses untuk produce induced EMF ah. Sebab nanti dalam next class misalkan minta someone explain again. So kalau kamu cakap clear, then next class misalkan tanya someone lah. Okay, so kalau tidak soalan untuk this one, so far kita hanya cover until coil saja. Coil pun the first example only. Nanti in the next class, I will cover for the conductor and the rotating coil. Okay, so no more question.
Tidak, Miss.
Question no.
Okay, kalau tidak soalan, I guess that's all for today. Okay, I will see you in the next class. Thank you.
Thank you, Miss.
Thank you.
Thank you, Miss.
Thank you, Miss. Thank you, Miss.
Thank you, Miss.
Thank you, Miss.
Thank you, Miss.
Um,
Thank you, Miss.